University of Kaohsiung. And all of you should introduce yourself. Okay. So from the reporter. Okay.
Hello everyone, we are your family and from Northern Senior High School. My name is Li Xingren and this is Guo Shenyu, 大约是吴云锦。
And reviewer.
Honorable jury and fellow competitors were Cynthia Leo from Garrison Senior High School and the team leader from England, Zhao Weizhi, Chai Rendao, Lin Xuyang, and Mo Weiwen.
And the opponent.
Honorable juries and all the competitors and leader of Team South Zero Bingxian and Team Strong Bingxian, Wu Hanshi, Wu Yizhen, and Chen Gayu.
So the judge will be Professor Chen Wenqi from Taiwan University and He Peimin and Su Wansheng and Xie Yating.
切马里奥，马里奥。
但是不一样。
他先生因为他不舒服。
哦，对，好。And the problem will be problem 9 as a team school. So the reporter got 5 minutes for preparation. Okay. Okay. You should write down the reporter and the opponent and your name. Now the reporter will floor.
Your honorable judges, opponents, and viewers. Today I'm going to talk about oscillating screw. My name is Typt and my team is very friendly for Russian Peninsula Russian Senior High School. So our outline first is a problem statement and then theory. Next is observation and then is the experiment setup, result, conclusion, and reference. So first, this is a problem statement. When placed on the side of the rim and released, a screw may experience growing oscillation as it travels down the rim. Investigate how the motion of the screw, as well as the growth of these oscillations, depends on the relevant parameters. This is my theory. So, according to this formula, potential energy and work of friction will equals to the kinetic energy of translation, rotation, and spin. So, to investigate the increased amplitude from period to period, we calculate the point from the turning point and to the next turning point. So, at the turning point, the rotation and spin velocity will be zero. So, because the amplitude is actually harder than just investigating the distance it goes to. We can use this formula to predict the amplitude for further experiments. And next, I'm going to talk about the motion of the rolling coil. So the motion of the rolling coil has two components: rotational motion around its own axis of symmetry and rotating motion of its axis around this axis of symmetry of the stationary cone. And this is the graph about it. So, omega 1 is the rotational axis, which is about this energy. And omega 2 is the spinning axis. This is my experiment setup. So first, we place the board on the middle stage and place our phone here, so we can record its motion simultaneously. So for further experiments, I will talk about the deflection angle, which is how the angle of how the screw goes down, and the angle between the board and screw, and the angle between the drum and the screw. So first, I'm going to talk about my observation of oscillating screw. The motion of the screw is way too fast to observe clearly. Since the screw itself is tiny and hard to adjust its size, we decided to model our screws to CD or plastic plates, which is more suitable to observe this phenomenon. However, after some experiments, we also found CD isn't a good model for oscillating screw, as CD is easily deviated from the original loop due to its larger size compared to both plastic plates and screws. So at first, we used a 1 meter board to conduct this experiment. We found that no matter what the deflection angle is, the period remains the same. However, CD has a great velocity of motion, and we couldn't generate enough data for the change of the amplitude by time. Therefore, we decided to use a board to change the screw for further experiments. So for experiment 1, I will talk about the deflection angle would affect the period of the change or amplitude of the oscillating screw. For control variable, the first one is the changes over time, like this. And so this is the deflection angle of 80 degrees and the deflection angle of 90 degrees. So to compare all the results, I draw it in a chart. And for the blue line, is 40 degrees and 50, 60, and 70, and 80. So we can know that the smaller degree of deflection angle, the higher increase of amplitude it offers. So for a reason, I think that smaller degrees will create bigger height difference. Since smaller degrees mean that it is like this, and so the height difference will be more bigger and will create more potential energy. For experiment 2, I'll talk about the angle between the screw and board. So my control variable is the board and the small screw, and angle between the board and the ground, which is 15 degrees, and the deflection angle, which is 60 degrees. And my independent variable is the angle between screw and ground. So here, this is a chart of the screw and the ground angle is 60 degrees, and this is the 50 degrees. So when the angle between the screw and the board is 40 degrees, which is the blue line, the amplitude increases significantly. When the angle between 50 degrees, between the screw and the board is 50 degrees, the amplitude always slightly increases. Now, when the angle between the screw and board is 60, the amplitude slightly decreases, but this is because the screws flip during this situation. So for why smaller degrees will create higher increase of amplitude? Well, I think that it is because smaller degrees create bigger height difference, just like the experiment 1. For experiment 3, I'm going to talk about the angle between the board and the ground which affects the period or the amplitude of the oscillating screw. So for control variable is the board, the small screw, and deflection angle is 60, and the angle between screw and ground, which is 45 degrees. So independent variable is the angle between the board and the ground. So this is the chart of the table. The angle between the ground and the table is 10, and this is the 15 degrees, and this is 20 degrees. So we found out that when the angle between the board and the ground is 10 degrees, the screw merely move. It is because that the friction is higher than the potential energy, so it didn't have the energy to slide. So this is the only difference at a y-axis movement compared to other charts. And so here is the table with the angle between the ground and the board is 15 degrees. So we found out that when the board and the ground is 15 degrees, only when the deflection angle is 10 to 60 degrees can make it slide down. When the degrees between the board and the ground is 20, only 10 to 40 can result the screw to slide down. So for my reason, I think it is because the potential energy is smaller than the friction. So the conclusion, the motion in which a screw moves down the rim and develops increasing oscillation is influenced by various factors. The first one is the raised angle. So the speed per ring will cause higher speed and amplitude oscillation compared to shallower rim. For deflection angle, smaller angle will result higher increase of amplitude the last one is the angle between the board and the ground, which is like if the angle between the board and ground is too small, the screw may not slide in. And thank you for your attention.
Okay, so thank you for your report. First of all, what is the main reason for the oscillation of the screw?
What is the
Main reason of the oscillation.
So when the screw is on this point, it will create the oscillation, and to balance the mass, it will close down. And
Okay, thank you. Do you consider the thickness of the top parts of the screw?
yes,
Thickness. You consider it in the cylinder part? Did you
Yes.
Okay, you consider it. And did you consider the thread of the screw?
the stress of
Thread.
the
Okay, we'll discuss it in the discussion. And since you assume the screw is like a cone, right, in your theory,
yes,
then there is how many contact points with the cone and the rack?
two
A cone and the rack.
contact points.
Yes. Okay. And that's okay. And so how many contact points is there? With the screw and the rack.
There's two, the
Okay.
upper point and the lower.
Okay. And do you think the friction acting on these 2 points will be different?
The friction. Yes, because the size is different.
Okay. And do you think the velocity of these 2 contact points will be different?
No, because it's actually the same item, and
So the velocity won't be different, right? Okay. Is it kinetic or static friction acting on the screw?
it is kinetic friction.
Okay. Do you consider rolling friction?
What is friction?
And what are the forces that acts on the screw, since you didn't mention that part?
The force, potential energy, and
Forces. Force.
the oscillating force.
Oscillating force. Okay. And do you think a normal force will be bigger on the top part or on the bottom part of the screw?
Okay, hands up.
Okay.
Okay, the opponent has 3 minutes for preparation. 台长。
Onward Reach and all compounder. I'm the opponent from Team Excelsior, opposing problem number 9, oscillating screw. This is a problem statement. When played on the side on the ramp and release, a screw may experience growing oscillation as it travels down the ramp. Investigates how the motion of the screw, as well as the growth of these oscillations, depend on the relevant parameters. So due to the problem statement, we mainly focus on how does the motion of the screw act, and in which situation that the screw will experience growing oscillation, and some relevant parameters that will affect the oscillation of the screw. So this is the outline of the reporter. So in the theory part, he assumed a screw as a cone, and she talked about the rotational velocity, also the period of oscillation. And then in the experiment part, she did several different parameters like deflection angle and inclination angle of the ramp. Also, he analyzed the coordinates of x and y axis of the screw. And these are the strong and weak points we believe the reporter did. So in the strong points, she has a well phenomenon explanation, and he explained the calculation well. However, I believe that she lacked of analysis of the motion of the screw. And also, she didn't consider lots of factors like the screw thread or the thickness. And she didn't mention how they consider the thread, just like I mentioned. And she didn't mention the releasing method. Also, she didn't calculate the boundary limits of these these phenomena. Since the problem statement mentioned, we need to investigate the growing oscillation. So there must be boundary limits of this phenomenon. So here are the points I'm going to discuss in this discussion. So in the first part, I'm going to discuss about the structure of a screw. So actually, the structure of a screw will affect the rotational inertia, like different structure of the head and the tail of the screw. So the reporter assumed it as a cone. However, in the reality, the screw is more like a combination of cylinders. So I will talk about how it's analyzed, how it affects the oscillation. And also the characteristic of the screw, like the center of the mass and the thickness of the head. Also about the screw thread, how will its radius and the thickness affect the oscillation. Also, I'm going to analyze about two contact points and how will the forces act on the two contact points, which is friction acts. And the friction includes kinetic friction, static friction, and rotational friction. And I would like to analyze these friction, which friction will act on the screw, and about its direction and magnitude. Then in the experiment part, I'm going to talk about the releasing method, because the initial condition seems to be a very important issue in this experiment. So I believe that there's a more stable way to release a screw to minimize the experimental error. And I'm going to talk about different parameters like deflection angle, inclination angle, and also friction coefficient. Then in the motion investigation, I'm going to discuss about the trajectory of the screw. And can the reporter's theory predict the motion and the trajectory. Also in the oscillation investigation, I'm going to discuss the oscillating angle and the problem statement mentioned about the growing oscillation. Also the angular acceleration of the screw, how well it's different as the initial condition differs. I'm going to discuss the phenomenon about overturning, also the boundary condition of this phenomenon. Thank you. So as I mentioned, I would like to discuss about the structure first. May I use the blackboard? Then use the blackboard. Thank you. And can you please turn to the part with the theory? Okay, so and we can discuss it on blackboard. So in a theory, you assume the theory has a cone, right? Like this.
No, actually, because there's 2 points, so actually it's like this.
Yes.
So there's a circle here, and there's a bigger circle.
Okay, so you in a theory you assume it's like this. do you agree with this? So
Actually, it is more like this. Here is more like this, but a smaller part.
So with the same contact surface, the friction will be the same, right?
Yes.
And however, you mentioned in the short question that with two different contact points, the friction will be different.
Wait, what I mean is because the surface of the air and here is different, so
Yes.
the friction, the energy of friction it causes will be different.
So the friction will be different.
Yes, but the coefficient is the same because it's the same material.
So in this part, I believe that the normal force on this part and this part is different. So the friction will be different. However, in their theory part, she cannot predict the motion of the real screw, right?
I could, because this measure is the surface.
But the friction is different.
The coefficient, the friction coefficient is the same, so you just need.
Yes. So actually, friction can be written like this. This is the coefficient of friction, and this is kinetic friction, and times normal force. However, the center of the mass is biased to one of the sides, which is more close to the head of the screw. So the normal force will be bigger in this part. Do you agree?
Yes.
So the friction is different. Do you agree?
Yes.
So I believe that the reporter's theory cannot predict the motion.
Wait, did I need to explain my
Okay.
formula? So here is the potential energy, and here is the work of friction.
So right. Okay, I understand that part. And do you have any comparison between the experiments and the theory?
Yes.
Since it's which part?
I didn't put it on my PPT because
So you have comparison, but you didn't put it on the PPT, right?
right.
Okay. And is there any deviation of the theory, or it's perfectly matched with them?
There is still some deviation, but
Okay, thank you. So the opponents still believe that as this model, it cannot predict the motion of a screw. Okay, I will discuss about the experiment part. Can you explain how do you release a screw?
put it on the board.
So you use your hands to release the screw. So the opponents believe that with using a hand, there might be a jack from the hand, and it might affect the initial condition of the screw. So I believe using an electrical magnet and to release a screw is a better way to release. Do you agree with my?
Yes.
Okay, so I think that you can optimize the experiment by using this method. Okay, and back to the force analysis. In the short question, the first question I asked is about what is the main reason for the oscillation. Can you explain that?
The main reason of oscillation is phase 5. First is the potential energy, and
Can
because
you explain that in the force analysis?
it will move down by potential energy, right? And here it will.
Also, do you mean that it's a move on by the gravitational component?
And it will oscillate like this, right?
Okay, the opponent, I agree with you. The opponent thinks, I understand the points of reporter. However, this is gravitational components instead of potential energy. Since energy is different from friction. And can you turn to page 17? And so in this part, you mentioned that the potential energy is smaller than friction. However, the energy cannot compare it with friction. So can you explain about that?
I mean, like the work of the friction.
Of the work of friction. So why do you think it can predict this phenomenon?
Because in here, it didn't slide down. So it only spins over, like it flipped. So
But why that spin over? Why will the coordinates of y-axis increase?
because it is actually really very good.
So will the screw oscillate down and oscillate backwards?
No, it didn't slide down.
It didn't slide down.
This is like very good.
And then can you explain about this part? Why is there like a gap between these 2 points?
Well, because because it didn't slide down and it also flipped down. So actually,
Since you mentioned about the flip of this phenomenon, which is same as the overturning I mentioned, can you explain about that? Why will the screw like? And may I draw the concept? So the screw will flip, right?
correct.
So what is the reason?
The reason is because when gravity is too energy is too small, the oscillation, like this phenomenon wouldn't be related to the problem statement.
This phenomenon wouldn't be related. But the problem statement mentioned that we need to analyze the growing oscillation.
Yes, but in here it flipped down, so its motion is actually not its amplitude rate.
Okay, so do you analyze the oscillating angle? Since you only analyze the trajectory, do you analyze the oscillating angle? Because the problem statement mentioned we need to analyze the motion, also the growing oscillation. Do you analyze the oscillating angle?
The oscillating angle,
Yes.
if I measure the amplitude, it actually can compare to the angle. Right? Because
Why? Not understood. The oscillating angle is like this part. So did you analyze this? Did you analyze this in the report? Sorry, did you analyze it in the report?
No, I didn't.
Okay, the opponents believe that we need to analyze the oscillation of the screw to match the problem statement mentioned. And do you think that there is a boundary condition for this phenomenon? Like the problem statement mentioned, it's need to be a growing oscillation. Is there a possibility that the oscillating angle will decrease?
There it is.
There is. Did you calculate the boundary limits?
Oh, well, it is at, wait, should I turn to the here, it decreased.
So do you have a critical value that at that point?
It's about 55 to 60.
So okay, you predict that value. And also, I agree with the reporter that there's the boundary limit exists in this phenomenon. So I would like to discuss about page 5. You keep mentioning about the energy transition. Can you explain how will the energy transist? Well, the potential energy transists into which kind of energy?
Potential energy goes the translation energy.
Translational. Well, so will the screw rotate by itself?
Yes.
So it will also transist to rotational energy, which I believe the reporter needs to discuss about this part. The energy, as it travels down a ramp, the potential energy will transist into kinetic energy and rotational energy, and also the energy friction consumes.
Okay, thanks.
And this is a discussion summary of my discussion. So in the first part, I discussed about the structure of the screw and how will the different contact points affect motion. And I believe that the model the reporter used cannot predict the motion, since there are two contact points and the model only has one contact point with the ramp. And the friction will be different on different contact points. And the reporter didn't show the comparison between a theory and an experiment. And I believe this part is very critical in presentation. I also mentioned about releasing method. I believe that we can use the electromagnet to control more safely. And it also talks about the overturning and flip situation, that an oscillating angle is bigger than 180 degrees. And the reporter didn't mention about the oscillating angle of the motion, but the problem statement asked we to mention and investigate that.
Thanks.
Okay, thank you for reporting. Upon the first question, I want to ask that, so what will cause the oscillation briefly?
Because the mass of it changes and
The mass changes.
The mass maintained, but in order to balance it, it will be
Okay, so do you agree to the report?
No, I didn't agree.
Okay, thank you. And next I want to ask that, so do you think that she used the rolling point is proper?
Rolling on, I mentioned in the discussion that
Yes.
I believe it's not proper.
Okay, so do you think that the opinion the opponent give is proper? That's because you only contacted 2 points.
because actually the screw when
And
it's
so
because it
will
only
you choose the rolling point or this one? Which is
What is-
much proper?
I think my model is
Your hand, okay, thank you. And next I want to ask that, so do you think when you release with pen, and you use pen to release the screw, is it proper?
well. I think
Yes.
maybe using magnet as well.
Okay, thank you. And next I want to ask that, and so what is the main parameters that will change oscillation?
I mentioned that,
Like what the main parameters?
okay, releasing angle,
Yes.
inclination angle, and friction coefficient.
Okay, thank you. And next I want to ask that, and so because you talk about the overturning,
Yes.
so what causes the overturning? Like
I
which
believe-
force or energy?
Gravitational components, when gravitational components, and as the releasing angle increase, the gravitational components will increase.
Okay, thank you. And next I want to ask that, so let's imagine there will be a boundary condition that the oscillation will decrease. So you said it's the 45 to 60 degrees.
About 55 to 60.
So do you agree with the reporter?
And in this condition, I agree with that.
Okay, thank you. So I want to ask that the friction for it is a static friction or kinetic friction? Kinetic friction. So do you agree with that?
Yes, I agree.
Thank you. And I want to ask what is the direction of friction?
The direction of friction is like just at the
Is this the opposite of the?
Yes, opposite.
Thank you. So will it be constant?
Will friction be constant?
Yes.
And at the same
Yes or
time, the friction will be constant.
Will be constant. Thank you. And next, I want to ask that, so when there is a growth of oscillation, do you think it is the gravitational potential or frictional power is bigger? Which one is bigger?
I think it's the first point.
Gravitational effect. Okay, thank you. And so, what do you think that caused the oscillation? Do you agree that it is a tangential velocity of the head and the rod that caused the difference? Tangential velocity caused the oscillation.
And I believe it's a gravitational components work on the,
It's okay. And next I want to ask that, and so if you discuss about the center of mass, so is the center of mass move like a straight line or what is the motion?
And like this.
Okay, so do you agree with the reporter?
yes, the center of the mass will oscillate as it travels down, remember?
Okay, so I want to ask your opinion about critique.
Okay, time's up. Okay, time's up. That's for the
Okay, thank you for reporting opponent, and I'm a reviewer from Together, and I'm going to review topic number 9, oscillating screw. So this is the problem statement that when you place iron side on a rim and release, a screw will experience growing oscillations as you travel down the rim. So in this problem, it's going to investigate the motion of a screw and the growth of these oscillations. So the main focus will be the motion of a screw and when we'll experience the growth of oscillation and the parameters that will influence the results. So here's my summary and comments for reporter. For the theory, she mentioned the energy transformation when during translation, rotation, and spin. And she also used rolling cone, but since that experiment only has 2 context points, so I don't think it is really proper. And next is the experiment for the tools. She used board, screw protractor, foam, and tracker for the motion analysis. And for the parameters, she changed the deflection angle, incline angle, and angle between board and ground. So this is the conclusion. When reached 60 degrees, the oscillation decreased due to the slipping. And the second is the oscillation increased because of gravitational potential is bigger than the friction of total work. So here's my comments for reporter. I think she has proper experimental setup and focus on the oscillating analysis, simple definition theories, detailed force analysis, and the suggestion will be that maybe there can be more about analysis for result and some comparison between the theory and the experiment. And also, I think the conclusion is hard to understand. So here's some of my comments for opponent. I think that he can really understand the reporter's report, can focus on the problem statement, can use drawing to clarify the discussion, and can also ask some significant questions. And some of my suggestion will be, maybe they can make sure the setup is proper or not, and don't ask parameters that the reporter didn't done. And also should focus more on the reporter's reports. So this is a review for the discussion. First question is that the comparison between rolling cone and screw discussed about context points. And reporter said that the friction of the 2 context points is different. My point is that both rolling cone and cylinder model require discussion on different friction, and rolling cone can be used as preliminary modeling. The second question is, do you agree that you should use electromagnets to release? And the reporter said yes. And I think that the opponent gave a good suggestion, but also should clarify the method he mentioned. And the third question is that what is the main reason of oscillation? The reporter said it's the initial gravitational torque to trigger the motion. And my point is that during the whole motion, torque caused by friction also contributed to the oscillation. And the fourth question is, what's your explanation of growing oscillations? The reporter said gravity, which from my point of view, I think it will be the tangential velocity difference. And the fifth question is, what is the boundary angle of the oscillation? The reporter said that according to the graph, it is between 55 and 60 degrees. And my point is that the critical angle should be measured as the boundary condition. And the sixth question is about the energy analysis. And the reporter said it is relevant, but no clear comment. And my point is that further calculation can be made to predict the motion. So here's some of my questions. First is, what will cause the oscillation? The reporter said gravity, and which I think will be a tangential velocity. And the second is, it is proper to use rolling cone. The reporter said yes, but opponent said no, which I agree with the opponent that maybe they should discuss about 2 different context points. The third question is, it is proper to release screw with hands. And the reporter said no, which I also think that they should use a magnet to release the screw. And the first question is, what causes the overturning? And opponent gives it is a gravitational component. And the fifth is, do you agree with the results of the graph that the reporter shown? And the opponent said that due to his experiment, he agrees. And the sixth question is, what is the direction of the friction? Well, the reporter gives me that it is the opposite direction of the motion. And the seventh is, it is gravity or friction is bigger while oscillating is growth, and the reporter is gravity. So here's some parameters experiment that I did a discussion and discuss. Thank you. This is my attention.
Okay, thanks. Now for the conclusion.
So first, we discussed about the main reasons of oscillation. So in my opinion, it is because that is the center of the mass. So you oscillate from height to that point down and go back. And the potential energy is smaller than the work of, when the potential energy is smaller than the work of the friction, it will cause this cause bigger angle. And so the reason why I choose to use a cone is because the friction of top and the bottom are the same coefficient. And also I observed that the thread of the screw didn't touch the board during the experiment. So I think that using a cone is proper for my experiment. And for conclusion, the reviewer said I wasn't clear of the conclusion, so I want to clarify more. So for deflection angle, which is how the screw slides down the board, so if the angle is more smaller, then the amplitude the increase of amplitude will be more than a bigger angle. And for angle between the screw and the board is 40 degrees and 150, while the 60 degrees isn't comparable because it eventually goes down.
Okay, hands up. So is there a question from the jury?
Would it work with an egg? And can you, sorry, you have used a screw. If you were to use an egg, an egg duct, would that work? And if so, that could you use the same approach to model it, or if not, why not? This is for, sorry.
I think using the egg will be not really proper since there's the attachment of the egg between the egg and board may not be the same. Moreover, the egg may break down because it is
So
like
you can use a boil. Okay.
So my point of view, maybe I think there is two different. First is the contact point, that there will be only one contact point. And the second is that because there is liquid in the egg, so I think the center of mass will change during the motion.
Yeah, so like I mentioned that the cone has one contact surface instead of two contact points. And so does the egg. The egg only has one contact surface instead of two contact points. And the friction will be different in the reality. However, with one contact surface, the egg will not predict our motion of the screw. Thank you.
So any other question? Using egg might be too expensive, too hard to find. So I'm curious is that how come people, so the experiment you did only try to vary the angle slope. Have you actually tried to think about using slope, using screw of a different weight? Or for example, like you can have a screw and then you have a clay putting on this screw and to change the center of mass of the total weight of the.
I think that changing the weight, changing the weight.
Okay, I mean, starting from the reporter.
I think changing of the weight, if I put on the clay, it will affect the center of the mass and result different kinds of motion.
It also change the normal forces, no? I mean, so you might change since many of you say the friction is quite important. So I'm just curious how come you didn't try to investigate how the friction or how this experiment might change if you change the shape of or the weight of the screw.
Because since I'm comparing the angle, I want to maintain the screw size and its attachment.
Yeah, but if you fix the slope and then change the weight instead, have you considered that?
We consider the slope of the.
Yeah, slightly different experiment, but it's equally relevant.
Yes, because the slope, I consider the slope by the angle between the board and the screw. Because to fix the angle between the board and screw, you need to move the plate forward.
What do you think?
So changing the weight will change the proportion of center of the mass and at least this kind of point and this kind of point. So the proportion of friction will be different. Also, by changing the weight, the length of the screw will also change different, and so it will cause a different rotational inertia.
Right. Okay. So have you done the same kind of experiment?
And so, do you mean changing the weight?
Question here is only, if you understand how this game is played, right? Question 9 is only just the words here. There are different ways of investigating this problem. I was curious about different things when we try different way of investigating this.
Do you mean parameters of changing?
Yeah, with changing weight.
Yes.
Even easier thing to do.
And we actually did in our experiments, and we found out that with changing the weight, the gravitational components will be bigger. So the screw duration that the screw slide down the ramp will be smaller because the acceleration of y-axis will be bigger.
So we also changed the mass in our experiment. That's why that it will change the friction force since it will change the normal force. And also it will also change the moment of inertia.
Okay, so how have you investigated this a little bit? Have you tried to do this experiment actually?
And yes, we actually do this in our experiments.
Oh, I see. So the conclusion is what? The heavier the screw or the shape of the screw, or how the weight is distribution, how is that affecting the, for example, the amplitude of oscillation?
I think that it will make the oscillation gets bigger over time since the moment of inertia also changes.
I see. So is it heavier or is it lighter or what?
Like when the mass is heavy.
Okay, thank you.
So score for the reporter. Right, 6, 6, 6, 7, 6. And the score for the opponent. This 1.5, is it?
No, 0.5, very 0.5.
Okay, 7, 6, 8, 7, 7. And the score for the reviewer. 7, 6, 7, 8, 8. Okay. So we can take a rest for 15 minutes. Opponent and reviewer to write out the main person. Okay. And now we will start to count. And the reporter got 5 minutes for preparation.
Yeah. I have to tell my student what CDs are. That's when you feel old. It's a state of it.
hands up.
Number 2 is another competitor. I'm the reporter from Team Excelsior, reporting problem number 4, kernel line. This is the problem statement. When the compact disc or DVD is illuminated with light coming from a film stem with such a way that only rays with large angles of incidence are selected, the clear green line can be observed. The color varies upon slightly changing the angle of the disc. Explain and investigate this phenomenon. So due to the problem statement, we mainly focus on why only specific colors were selected, and why the colors vary by slightly turning the disc, and what is the composition of the color. So this is the outline of our report. So first of all, in the observation part, I separated the phenomenon into 2 stages, and clear green line and color change. And in the experiment part, explanation part, I'm going to give my qualitative explanation and also my theory about light class difference. And the analysis of color change, I'm going to do 2 different parameters: tilting angle, rotating angle, and how I use laser to calibrate. And the third parameter is about the comparison between CD and DVD. So this is the observation. So this is the experimental setup of my experiment. So I use a camera and a filament lamp whose is 1.5 meters away with the CD. And I use a motor and Arduino to control the tilting angle of the CD accurately. And this is how I analyze the color. So I obtain the RGB value of the color, and I use the color library in Python to get the dominant wavelength. So this is the CI coordinates of the color. And by connecting to a white point, we can get the dominant wavelength in this picture is 551 nanometers. And this is the 2 stages I'm going to introduce. So in stage 1, the clear green line can be observed when the tilting angle is small. And in the second stage, when we increase the tilting angle, the color will vary from turning a disc. And in this section, green line can be observed multiple times. And I consider the wavelengths of visible lights as 400 to 700. And in this case, the wavelength of green lights is 527 nanometers. And this is the explanation. So this is a micro scale of a CD. You can see that there are several checks on the backside of the CD. And the checks are equidistantly distributed with a distance of 1.6 micrometers. So when the light is illuminated to the back of the CD, it will generate a 2-wave that is in phase. And it will create constructed interference with the light path difference equal to 1.58 in this situation, which is the horizontal component of the distance between adjacent checks. So with a multiple value of m, which is the wavelength that consists in 1 light path difference, we can obtain these several wavelengths. So this is a qualitative explanation of the second stage, which is color changing. So if we increase the tilting angle, and the horizontal components of the distance will be smaller. Also, the light path difference will be smaller. So with the same tilting angle and same value, with the bigger tilting angle and same value of m, the wavelength will be shorter. So we consider it as when the visible wavelength is 400 to 700. So this is a theory of my experiment, and that's a theory of this phenomenon. So if we give this a tilting angle alpha, from viewing from the side, the light path difference then become A cosine alpha. And from viewing from the top, the beta is half of the included angle between observer and the light source. So the light path difference will become A cosine beta. And by combining 2 of them, we can get the light path difference as A cosine alpha cosine beta. Then by this equation, we can obtain the value of wavelengths. And this is the analysis of color changing. So by comparing to the experiments in the theory, we found out that there is some deviation in this part. So in the first part, there's an increasing wavelength, which is against our expectation that the wavelength should decrease while tilting angle increase, because it's the cosine properties of mathematical properties of cosine.
And there's a missing wavelength in this part. And there is several unexpected wavelengths that is not on the theory line. So let's discuss the missing wavelength first. So if we zoom out the chart, we found out that actually the missing wavelength is not actually missing in this chart. It's negative wavelength that's around here. So why will this phenomenon happen? So we picked one of the missing wavelength or negative wavelengths to analyze it. And we found out that in this tilting angle, the color on the CD is purple. And by comparing to the CI coordinates, the CI coordinates of the color is right there. And by connecting to the y points, we found out that dominant wavelength cannot be found, since this line there's no dominant wavelength in this line. And so the Python tends to find the complementary wavelengths. So it's called negative wavelengths. And it can also prove that the color on the disk is non-monochromatic, which is composed of various different colors. So by knowing this, we optimize our experiment by using a prism to explain the negative and increasing wavelength. Since both of them is the reason of both of them is because the color is actually a composition of various different colors. So by using prism, we can separate the purple into these two colors, red and blue. And this is when tilting angle increased, the color with prism will look like this. And there's also one problem we haven't solved. It's about the unexpected wavelength that is not on the zero line. So we solve it by using cross-check interference. So actually, in our theory, we assume that every light that construction interference is generated by adjacent checks. However, there's a possibility that the constructed wave might be crossing various different checks. So we assume the value k is how many checks, the amount of checks the constructed wave cross. So in this case, when k equals 1, the theory line will look like this. When k equals 2, 3, and so on and so forth. And as the overlaps, as the k value decreases, the overlap time will increase. So we consider k equals 1 and 2 because the intensity is bigger because it has been overlapped for more time. So this is k equals 1, and this is k equals 2. So by analyzing the experiment with prism and cross-check interference, and without prism and also without cross-check interference, we found out that the unexpected wavelength has been solved by cross-check intervention. And the wavelength decreased as the tilting angle increased, which matched with our expectation that the cosine value. And with the prism, the light can be separated into several different colors. Like in this angle, the light is actually composed of 3 different colors. And the slope will get steeper while the tilting angle increases because of the mathematical properties of cosine. And this is the second parameter about rotating angle. So we define rotating angle as half of the included angle between observer and light source. And beta is also the cosine value here. So when rotating angle increases, the wavelength will decrease. And this is the light path difference. However, we found out that actually in these parts, there are several parts that is flattened, which is not, which is against our expectation. So we go back to see the first parameter about tilting angle. Actually, you find out that there is the same problem here, that wavelength is flattened instead of decreasing. Also here. And actually, this phenomenon is caused by the photosensitive elements of camera, because it is inaccurate with some light. So we use laser calibration to fix that. So we project 2 kinds of laser in the center of the disk. And because the laser has a fixed wavelength, so due to the refraction difference, it will refract to a certain location. And we use inner division points to obtain the wavelength of the light. So you can see that experiments with laser calibration and experiments without laser calibration the flattened part is solved. And also, and most of the experimental data fits and match with our experiment well. So this is the analysis of tilting angle. So in the first part, the light is actually composed of 2 different colors. And in the second part, the light is composed of 3 different colors. However, it's shown on this green light because the relative intensity is bigger. And there's a missing wavelength because it's a composition of red and blue lights. And this is a comparison between CD and DVD. So actually, DVD has a smaller distance between adjacent tracks, which is 0.74 micrometers. So you can see that when the same value of tilting angle in a small tilting angle, and also the same value of M, we found out that in this part it's blue light, however in the CD it's green light. And this is my conclusion. So why do we see a green line? So actually the reason we see a green line is because the uneven surface on the back of the CD, which means the tracks on the CD right there. So it will generate a constructive wave. And how do we analyze the experiment? So originally we used RGB value and CI coordinate. However, we found out there's some, the photosensitive element is inaccurate. So we use laser calibration to fix that. And due to the refraction difference, we can obtain the wavelength. And this is the conclusion of tilting angle. So the light path difference will decrease while the tilting angle increase. And also, it's caused a constructed interference wavelength to be different. And finally, we get that the wavelengths fit and our experimental data fit and match with our theory very well. Thank you.
Very nice job. Now for the reflection.
Thank you for your presentation. Your comments and some questions about your presentation. First of all, please turn to page 8. Okay, this page? Yes, I mean, okay. Now, so in this graph, you define your horizontal axis as tilting angle and the wavelength here, right? Correct. Okay. So can you illustrate what is your definition of tilting angle again?
Okay. So tilting angle is actually, so this is a horizontal.
Yes.
When tilting angle equals 0.
Yes.
So when it's increased.
Yes, you answer the question. Now, can you please go to page 6? 6. Yes. Okay. So here you have the CIDX and CIDY. So can you briefly define what is your definition of the X, Y axis?
So actually, the CI coordinates have 3 different coordinates that X, Y, Z. And X plus Y plus Z equals to 1. And because this is actually related to RGB value.
Please let me rephrase my question.
Okay.
Is X and Y related to the real geometrical world from here, like X and Y?
Oh, no. This is a CI coordinates that is specific to analyze the wavelengths of the
Well,
object.
that's for a later discussion.
Okay.
Now, please turn to page 20. I think I will test it by myself. As you mentioned, use the filament lens. Use the filament lens, right?
Yes.
Okay, so
Okay,
so is the filament lens coherent?
Coherent.
Yes, coherent. Yes, it is coherent. Okay, thank you. And now please go back to page 8. Page 6. Excuse me. Okay, so here you have some blank parts of the graph. So can you explain why these arrows are blank?
Do you mean this? Oh, this is the limitation of CI coordinates since it says X and Y and Z.
Okay, thank you.
student from Team Galileo, and today I will pose question 4, color line. And this is a problem statement. The main focus provided in the reporter's report is why only specific colors are selected, and color change must likely change the angle and also the composition of the lights. And we believe that the main focus on the presentation has this requirement that only large angles of incidence are selected, and we also have to explain why only green lights can be observed. And also, it requires us to investigate a situation in which light will change the angle of the disk. So here is an outline of the reporter's report. First of all, in theory, they introduced a periodic structure which can be observed in a CD, and also they have some graph about the light waves. So they have constructed an interference which is demonstrated in their presentation, and also they use a prism to analyze the components of light. And for the experiments, the tools they use a filament lamp to create the source of the light, which is also mentioned in the problem statements. And they also use the camera and CD to conduct their experiments. And for the parameters, they have conducted experiments according to tilting angle, and they have the conclusion that the color of the light may change when we change the tilting angle. And also they use the prism to analyze the components of light. And also they define another rotating angle. And for the analysis, they use the CIE chromatic variable for the comparison. However, we believe that this will require some further discussion. And for the conclusion, they say they see a green light because of constructive wave, and the tilting angle increases, light path differences increases, and that's how they explain why you see a different color when you change the tilting angle. However, in the experiments, I think there might need maybe an explanation to explain why we only observe the light, and the light is towards the diameter of the disk. And here are some suggestions and the pros and suggestions and strengths of the reporter's report. For the pros, he has a theoretical model to compare with his experiments, and he also has detailed theories to explain his phenomenon, which he used is the interference of the light and the optical path difference. And also he can explain in what condition different colors can come out, and he can also find out the errors why the data doesn't fit with the theoretical lines, and he also has a way to fix it. And first of all, he did not explain why there is a line toward the diameter observed, and also the definition of light color may use the RGB to express. And also in the theory line, I believe that there wasn't any mathematical expression for the theory model for the theory curve. So here will basically be the discussion, which will lead to later. First, for the phenomenon, we will discuss a straight line and why a green color can be observed. And for the theory, first they introduce the conception of a periodic structure, which we may use another noun, which is diffraction grating, and also the constructive interference that may cause a different color we observe. And also we will discuss what the function of a prism and what we can know from the analysis of the color. And also, as the short question parts, the reporter answered that the filament light is a coherent light, but I believe that there requires some additional discussion about the coherence of filament lights. Okay, I'd like to start my discussion with the reporter now. Okay, so may you please go to page 8. Okay, so here, your tilting angle in your model, here is your tilting angle, and as you change your tilting angle, you can observe a different color. Yes. However, in some stages, you can see multiple colors on a straight line. So, however, at the wavelength here, for every tilting angle, there is only one corresponding point. So how do you determine which wavelength you will observe?
Okay, so actually we control the camera and the CD as the same surface. So we control the same surface in this part. So we analyze the color on this point because it is on the same surface, which is the most accurate.
So can you qualitatively describe this point?
What do you mean?
Quantitatively, for example, how many centimeters from the center of the
So do you mean the camera with the distance?
No, I mean, since you just mentioned that you only analyze
to the center of the disc on the upper part.
Okay. So that's how you select your wavelength.
Yes, because the CD and the camera is in the same surface with this part.
So where did you place your light source in this example?
So actually, there's a requirement to fulfill in the experiment because we need to control rotating angle. So the light source and the camera need to be very small. The distance between light source and camera need to be very small.
And can you define your rotating angle again?
Okay. Can you please turn to the page with can we use the blackboard to?
Okay.
So that's defined a light source as S.
Yes.
And the observer as O.
Yes.
So this is CD or DVD this. So actually the beta is like this is a line.
Yes.
So the beta is this is a point this is a point we observe.
Yes.
So the beta is in this angle. Which is the rotating angle.
Okay, so here is your definition of the rotating angle. So basically, okay, so you define this angle as rotating angle. So when I ask how do you determine this axis?
How do I determine the
Yes.
axis?
What is
So,
this axis?
so actually the angle between this angle and this angle need to be the same.
They always have to be the same.
Yes, because to generate the line on the CD, the distance between adjacent tracks need to be different. So as the tracks is like circular, this like the tracks is on yes. So the distance between each of them need to be the same.
Okay, so as you just stated, that the two angles of the spectrum should be the same. Okay, so may I ask what if the baseline is different? For example, if I stand here, what will I see?
What did you mean?
Yes.
Yeah. So where?
Yes. So you say that this two angle is the same. So if I stand here, that this angle is the
This
same.
angle is on this.
For example, like this.
So can I draw a different? So
Okay.
Okay. So like this and from this, and the line will probably be on this part.
Okay. So since you just mentioned in this graph, so I want to ask another question. Okay. What is the reason that you think that we can only observe a straight line on this distance?
As I mentioned here, the distance between adjacent tracks need to be the same. So if we like this one, we cannot observe the line on this part. Do you get my point?
Well,
Like this is the line source.
well, actually, I don't. Well, first, okay, so so let's draw the. So now can you please explain why we don't observe three lines here? So here, as we say, since if we only observe the green light, which means that this is the source of the light,
So
and this is the observer, which means that only light from this direction can reflect
yes.
to the observer, is that correct? However, my point is, if there is another light from here, and it hits some points right here, and it goes to the observer, it is still possible to fix the requirements.
So
the
actually-
angles are the same. So I would ask that since this is also possible, so why can only the lines where the diameter can be observed?
So actually, the line won't be on a different surface except the diameter. The line will always be on diameter because.
Okay, please.
Okay, thank you. So it's okay. So actually, the tracks the distance between adjacent tracks need to be the same to observe a line. So actually, the distance between this track can generate a constructed wave.
Okay. So in your opinion, the reason that why we can observe a straight line is because of the interference of the lines, right?
Yeah.
Interference.
The constructed wave.
Okay, so this is one explanation about that. Since since you just mentioned the conception of the periodic structure, such as the this one, and when we zoom in, then we can see that the structure here is actually not really periodic. So that's the reason the diffraction, which is also interference, cannot be observed. So that is my explanation for why we need to, why the light is open and damaged, which is really similar to your explanation.
So do you agree with my explanation?
Yes, and okay. Thank you. And sorry for my accent. Yes. Okay, so now I believe we can move back to the.
Okay.
Yeah. Okay. So now can you please turn to this picture? You have many curves. You have many theoretical curves here. So can you describe each of the curve with a mathematical function?
Okay. As I mentioned in the report, that actually this flattened part is caused by the photosensitive.
No, I'm asking each theoretical curve, can it be expressed with a mathematical function?
It's our zero line.
Okay, so the reason why we have different curves is because we have
Different value of
n.
yes.
Thank you. So can you explain why the deviation of here is quite big?
Do you mean this arrow bar?
Yes.
Okay, so actually the arrow bar is caused by, this is like a border between green and yellow lights. And the camera will tend to fix the lights to yellow or green because of the photosensitive element, which causes deviation here.
Okay.
Can you understand?
Okay, so what difference do you mean by? Okay, so what's okay, thank you. So in your laser experiments, you have fixed this problem, right? So can you tell me the difference between this experiment and the experiments you used to fix your theoretical, please?
So we actually use a difference analyzing method. So in this part, we use the laser calibration, which will not cause by a difference between the photosensitive elements because we use the location of red and blue lights here and using interdivision points. And because we use the camera, it won't affect the location or proportion between the green line or the red light. Did that answer your question?
Well, I mean, this calibration here, can you explain this word? Calibration.
So explain this calibration.
Yes.
Okay, so we project two kinds of laser. So a laser actually has a fixed wavelength. So
the light
the red
source
part
here is a laser, not a filament lamp. The light source you use in this location is
So-
still a filament
So actually, filament lamp is a continuous spectrum, which contains each of the wavelengths in the visible light. So we use laser to make sure the location of the particular wavelengths.
Okay, so is the light source you use to observe the green light still a filament lamp in this experience?
Yes, yes.
Okay, thank you. So as you just mentioned in our short question, you think that the filament lamp is a coherent light, right? Okay, so please, do you understand my term of coherence?
You can explain that.
Okay, coherence light, which means the two light sources they don't have any phase difference, which means that two lights that can move in this, so they don't have any phase difference. And only under this condition, then in your model you mentioned that the optical path difference has to be an integer of the wavelength, so that
Okay, and there's the difference.
Okay, so now my question is, can you make sure your filament light is coherent?
So I agree with your point that so actually the light wave that generates by the uneven surface will in phase.
So is it coherent? Is it still coherent? Is your light source coherent?
So in this case, this is not coherent. If your definition of coherent light.
No, I mean the source of your light is a coherent light.
Yes. So according to your definition and this phenomenon, it won't be coherent.
It won't be coherent, but however, the interference effects can still be observed. So you have an explanation for that.
And so I just making sure that the definition of coherent light in your definition is that it won't be in phase, right?
No, it means that it doesn't have any phase difference.
It won't
phase
have.
difference.
Okay.
Do you understand this from phase?
Yes.
So as you just stated, that is not a coherent light.
Okay, time's up. So we are gonna to summarize.
Okay, so during this discussion, we have some discussion about the theory and the explanation of the graphs. And for the theory parts, the opponent believes that we have an agreement that y only a line toward the diameter can be observed, which is due to the periodic structure on the disk. And also for the theoretical line, the opponent verified that each of the theoretical line is corresponding to an integer m. And also for the experiments, since in the short question term the opponent replied that the filament line is coherent, but in the opponent's opinion, I don't think that is a coherent light. So I think it needs a further explanation for why we can really observe a green light on the disk, since if it's not a coherent light, from some experiments we can know that the effects of interference is not so obvious. So I think that there might be a slight problem if we want to describe this phenomenon with the interference of light, since the light is not coherent. Thank you.
Okay. Now you will have more.
I want to ask you both, do you think the scattering is one of the reasons that influence the experiment?
Well, I think that, can you define scattering? Because I never heard that word before.
Okay, scattering, how?
Can you give the word definition? Do you mean the environment of the experiment?
How about, do you think refraction will may influence the experiment?
Well, I don't think the refraction is the main reason of this phenomenon. Instead, I think the reflection of the light may have contributed to this phenomenon.
Refraction, yes. As I mentioned, that uneven surface, and so it will generate a constructive wave. So do you mean this kind of refraction, or?
I think when the light put in on the refraction, the blue light is because of refraction. Okay, never mind. Okay. So the CD and the prism can separate the light. Do you think they are the same phenomenon?
The CD and the prism.
Yes.
So we use a prism to separate the purple light or the.
It's the same phenomenon.
Do you mean by CD, like by prism?
Yes.
So the CD is actually the color we observe, and the prism is a experimental method we use. It's different.
It's different phenomenon.
What do you mean by different phenomenon?
Why they separate the light?
No, it's different.
Well, I don't think that the experiments of CD and the prism can be categorized as the same phenomenon, since one is related to the interference of the light and the other one is only refraction.
Okay, do you think CD and burn CD is different in the experiment?
CD and burn CD?
Yes.
So actually burn
Blank
CD.
CD and burn CD. Blank CD.
Okay. So burn CD will affect the light intensity, but I believe it won't change the wavelength much.
Okay.
Well, I think the difference between the burn CD and burn CD is due to the digits between when CD is burned or unturned. Maybe have opposites.
Okay.
I know.
When the angle is to be the reflection may influence the observation, how did you deal with it?
So
Reflection to be.
and do you mean
Reflection.
You mentioned the angle is too big, like this. So actually we cannot observe a curved line in like 88 degree and 90 degree.
Okay.
Well, I think when the angle is big, you can observe multiple colors on a straight line.
Okay, thank you.
Thank you.
Okay, I'm done. Okay, I'm going to review the color line. Our statement when the context is or image is diffused with light coming from a lemon lake in such a way that only rays with large angles of incidence are selected. A clear green line can be observed. The color varies upon slightly changing the angle of the display and investigate this phenomenon. We may focus on when the specific color are selected and why the color varies by slightly turning the disc and what is the composition of the light. Okay, and the summary of the report. They say they analyzing method by Phison and CIE, chromatically different and color changing. The wavelength will be shorter in smaller angle, and the wavelength decrease as the tilting angle increase. And the reason why seeing a green light is because the surface of the disc attracts the wavelength of green light. The parameter is the tilting angle with or without prism and rotating angle. Conclusion is see a green light caused by the constructed angle. And overall, the reporter they close because they follow theory and investigating about the missing point and a clear effective explanation. And they fix the deviation by changing the source of the light, but the icons didn't include their experiment model and didn't focus on green light and no mathematical expression of theory model. And over the moment, consider how different position of observation will affect the result. Discuss about the cause of the green street light despite just considering the constructed inference. But they also didn't focus on the experimental process. Also, okay, it's a light conference report. Report say no, but we see the phenomenon occurs by the conference light. And how do you compare with the phenomenon of the straight line by observing one point? The point in the straight line reflects the same wavelength as the light. The rainbow light, this is our question. The rainbow light by the prism is in the same phenomenon. We'll say no, and it's different price. Prism separates light by refraction, but this is separated by diffraction. Do you think this reflection creates the green light? They say no. How did you deal with a strong refraction when it's strong observation? Reporters say it can be seen, and we'll see we can just adjust the light's intensity. And do you think blend CD and burn CD or BT is different in experiments? Reporters say won't change the very much, and opponents say yes. And there are differences in experiments we see because from the CD will change its surface and influence the diffraction. Let me see point they didn't focus on the green light much when they are discussing. Thank you.
Other trees and other competitor. This is a concluding remark from the reporter. So thank you for the opponents and the reviewer for giving the suggestion. So first of all, we control the disk and the light source on the same surface to reduce the experimental error from different viewing angle. And we define the beta angle as a rotating angle, which is the half of the included angle between the CD and the light source. And the distance between adjacent tracks need to be the same to cause a straight line on the CD or DVD, as Problem 7 mentioned. And the arrow bar is caused by photosensitive elements of the camera. So actually there are several photosensitive elements or like white balance will affect the color to be seen on the photo from the reality. So we use laser calibration to fix that. And we use, like this part, we use laser only for calibrating the experiment to ensure it won't be affected by the photosensitive elements. However, the green line and the experimental data is still use filaments which the problem statement asks. And the UCD will change the light intensity but won't change the wavelength much. And we control the distance of the light source observer and the CD. So the distance between the light source and the observer need to be small enough to ignore a rotating angle with doing an experiment about tilting angle. And the CD and the observer or light source need to be long enough to ignore the difference. And laser calibration is the correct way to analyze the color by using interdivision points. And we can find the wavelength and the location. And we put the equation of wavelength in the theory part several times, which invariably we didn't do that. And actually, we put it on the top part, also this part of the slides to emphasize.
Okay, thanks up. Is there any question from the jury?
Why does the question, sorry, this is a question to everyone because, okay, anyways. Why does the question of the problem focus on large angles? What is it that all of you have overlooked in the setup of a CD? Sorry.
So actually,
Sorry, let me phrase it more constructively. What else is in a CD except a reflective surface?
sorry.
What else is in a CD except for a reflective surface?
Do you mean the structure of the CD?
Yes, please.
And can you turn to the backup page? So actually, the structure of a CD can be separated into several layers.
Okay, so because we don't have time, but how would that change? What else would you have to consider for large incident angles compared to for very small ones?
So the first statement mentioned that with a large incident angle, a clear green line can be observed.
The what thing?
A clear green line.
Okay.
Can be observed.
Let's.
It's-
Sorry, I should consider the
I think that besides the reflection surface, we also have to consider the diffraction grating like structure inside the CD that it causes, which we believe is the main reason why we can observe the green lights.
Okay.
Okay, because of the holes on the CD surface and in a big angle, a small angle, it can refraction, and because of incurrence, and we can see the clear green line.
Any other question?
Can I ask another one?
Yeah, of course.
Do you know what total internal reflection is? Total internal reflection. We're going to start with
Okay, so total internal, is that reflection?
reflection.
Reflection is that when the okay, maybe I forgot the name for that, but when you have the lights and from one one medium to another one, and when this angle is large enough, it will not refract, only reflects back. And that is my understanding.
Yes, I agree with the opponent that with this condition, which is total reflection, it won't refract, but it will totally reflect back.
Okay.
Okay, because the surface looks like this, right?
Sorry.
Okay, and the light, if the light go in this, and will not refraction, it will not refract, will not refraction more, and reflection is more, and we will not see the refraction.
Okay. Any other? Okay, no. Okay, the score for the reporter. 86876. And the score for the opponent. 87883. And it's all for the reviewer. 76773. So, how can you explain?
Yes.
how,
This process is very different. You have described the rainbow, which is this is refraction. Sorry, this is diffraction. But the point is that the CD, if you're shining from the side, is like a waveguide. A waveguide is a structure that has a high index of refraction, not diffraction, and light is trapped in there. And so the light will travel unless it hits the bottom where you have now a grating. And so that will get the light out. So you have done a beautiful job to describe a grating. But it's not a grating, it's a grating inside a waveguide. So you missed the point of the large angle, I think. And so that's also why you see all the different colors of the rainbow, right? The question was, why is there green? Right? That's because that one will be the only one that will come out at the critical angle. So it was a good question.
And the other text for aberration. And Typt, you write down the main person and on the breadboard.
Okay, thanks, Doc.
Honorable jury and fellow competitors, I'm the reporter from Team Galileo. Today I will report problem 6, magnetic mechanical oscillator. And this is the problem statement. Secure the lower ends of two identical leaf springs to a non-magnetic base and attach magnets to the upper ends such that they repel and are free to move. Investigate how the movement of the springs depends on relevant parameters. So here is our preliminary observation. We attach two magnets to the upper ends of the rollers, and the rollers here can be viewed as leaf springs. And we then release the magnets, and then we observe the motion. We use the tracker to track the magnets, and we sketch the graph of the motion, which is demonstrated here. From these graphs, we can see that the oscillation amplitude jumps away as time evolves, and the energy seems to transfer from one to another, since when the blue curve has the biggest amplitude, the red one has the smallest. And this is the video. And for our parts of theoretical derivation, since we're dealing with an oscillation here, so we'd like to consider the simplest model of the oscillation. So here we consider a single magnetic oscillator, and we also take the air resistance into the account. So here we consider a mass spring system with a mass m and the elastic coefficients k. And we can write down the equation of motion by carrying out the force analysis, where beta is the coefficient of the air resistance and k is this k. And after we solve this equation of motion, we can obtain the expression of the displacement, which is a damped cosine function, where omega equals to this term, and omega naught is the natural frequency of this of the mass spring system, and gamma is a constant defined by beta over m. And here, we numerically use the trajectories to find the omega naught and gamma by using the last example. And from the blue dots are the data, and the red one is the fitting curve. And our fitting results with gamma is 0.33, and the omega naught is 13.6 radian per second. So here is the leaf spring system and mass spring system. Since a leaf spring system is not a simple mass spring system as we consider in the theoretical model, so here we will have to measure the effective coefficient k and the effective m. And from our fitting results, our effective coefficient k is 7.9 newton per meter, and the mass is 4.27 gram. And here we can start to consider a coupled system. A coupled system is defined as when the member of the system when they interact with each other. So here the coupling term is the coupling is caused by a spring. So we can again write down the equation of motion. And here we have to know that the mass of the two objects are the same. And we can take the sum and the difference of these equations and obtain two different angular frequency. And we may note that the omega x is only relevant to the spring here, and the omega x is also relevant to the coupling term. So this part of the theoretical derivation, we will consider two special examples. For the symmetric mode, which the omega s is only which is shown here, and the antisymmetric mode is the one frequency shown here. And the phase difference of this is 0 and this is pi. So here we'd like to write down the general expression of the displacements of the two magnets. So here we can take the plus or minus 1 here so that we can express x1 or x2. And we can obviously see that the x1 and x2 can be expressed by the combination, two linear combination of the sine function of different angular frequencies. And here is the sum product identity of trigonometric function. And additionally, when omega s is approximately equal to omega f, then we know that a beat frequency can be observed. And the beat frequency here is the absolute value of the difference of omega s and omega x. And here we'd like to show the comparison between the magnets and the springs. And we know that the relation between the repelling magnetic force and the distance is not linear, when we know that the relation between the spring force and the distance is linear. So we require a correction of our theoretical model, that we cannot just use the magnets as our model, we have to correct it into the magnetic term. So here we can approximate the magnetic force between the magnets by this formula, which is obtained from the references right here. And the second approximation and the magnitude of the force decrease when the distance is further. And for our experiments, for the convenience to fit, we can introduce another notation, kappa. And the kappa is the magnetic coupling strength, and this epsilon here is the regularization constant factor to prevent that if the denominator is 0 when x is 0. So here is our experiments and theoretical observation. In our experiments, we approach one magnet to the other one, which is attached on the string. So that since they repel each other, so there will be an induced displacement x. So here is the relation between the induced displacement x and the magnetic distance. And this is the previous fitting result. And then we can measure the effective magnetic force. And finally, we can start our fitting procedure and have a fitting curve. Okay, so our fitting results, kappa is 73.631, and the epsilon here is 4.45 centimeters. Okay, so now we can finally write down our equation of motion. In our equation of motion, this is a net force M, and the net force can be divided into 3 parts. The first part is caused by the spring force, and the second part is caused by the damping, and the third part is caused by the magnetic coupling. And we have to numerically solve this equation of motion. And then here is the code that we use to solve the equation of motion. And we also can sketch the graph of the axis into like x1 and x2. And obviously, the lead frequency can be observed in our example. And also, we can use the fast Fourier transform to obtain the 2 normal mode frequencies of the components. So here is our experimental setup and methods. As we mentioned in our observation, we use the magnets and the lead string, and we also attach the magnets to the end so that we can verify the initial displacements. And we use a tractor to analyze the motion, and we use the Python to carry out the Fourier transform. And the left-hand side is our theoretical curve, and the right-hand side is our experimental curve. We can see that the results, they highly agree with each other. And here is our first set of experiments is considering the initial displacements. And here we want to verify the relation between the initial displacements and the angular frequencies. And from our equation of motion, we predict that it's irrelevant because we don't see any relevant term here. So here is our results of the initial displacement, which is 1.1 centimeter. And these two are the component frequencies. And this is the example of 1.5 centimeters and 2.2 centimeters. So from here, we can see that since the 2 components of the frequencies are the same, so we can say that the angular frequency here is irrelevant to the initial displacements, no matter how close or far you separate each one with your hands or your equipment. And the second experiment, we want to verify the connection between the magnetic strength kappa and the angular frequency. So here, what we're changing is the magnetic coupling, and we vary the coupling strength by changing the number of magnets, and we keep the mass the same. So here is our example of 1 magnet, and 2 magnets, and 3 magnets, and 4 magnets. So from here, we can see that only one of the two frequencies change as we add up the amount of magnets. And here is the experimental results and the graph here. And in our third set of experiments, we want to verify the connection between the initial displacement state. And here we vary the coupling strength by changing the distance, and we keep everything else the same, including the mass and the material of the 2 leaf springs. So here is the example of 2.6 centimeter and 2.2 centimeter. You can also see that only one of the 2 frequencies has a displacement. And the example of 2 centimeter and 1.6 centimeters here. And from here, we can see that the coupling effect is not so obvious, since we mentioned in our previous presentation that the frequency can be observed when the omega s and omega f are similar. So from here, the difference is quite big. So it is reasonable that the coupling effect is not so obvious. And this is our experimental results. And here, since only one of the 2 frequencies, the change. So this model is really similar to the model in which we consider the spring as a coupling effect. So here we use here carries a comparison between the magnetic interaction and spring interaction and the Taylor expansion approximation by ignoring the higher order terms. So here the first term can be written as a series, and after we ignore the higher order term, and the second approximation can be made. And we can rewrite this term as a kappa prime. So now our initial magnetic interaction can be approximated into a spring-like interaction. So this is our initial statement, and this is our then we approximate it using the magnetic term. So our second is this term in the normal modes, which is already mentioned in the previous discussion. So the symmetric mode is where delta phi is 0, and this one is delta phi equals pi. And also there's no reason observed in this examples. So this is a symmetric mode. Only one beat of frequency, and the other one is the other beat of the frequency. So this is our conclusion for the phenomenon part. The oscillation transfers from one to another, and we can also observe these in the trajectory. And for the theory parts, we have the equation of motion, and the term of magnetic coupling can be rewritten into the spring-like term. And for the experiments, the only affecting parameter is the Coulomb strength. And for the discussion, we have the symmetric mode and anti-symmetric mode. And the symmetric mode is written as this, and the omega 2, the other one, can be written as this term. And that's all on my presentation. Thank you for your attention.
Okay, so now for the component.
Okay, so for the first question, what factor do you think will cause oscillation?
Okay, so from here, since we have there's a leaf spring and the magnets and they repel with each other. So in the leaf spring, it has this force to return to its initial state. So that's how it causes the oscillation, the origin of the oscillation.
So the force to return is the main cause.
Yes, that's my opinion. That basically is the force that return can generate all the oscillation, and the magnetic coupling term is the reason that why we can observe the beat frequency.
Okay, and I would like to see your experimental setup.
Okay. In this page.
Yes. The two magnets, their distance is very close. So will they beat each other?
Do you mean that the two magnets are really close with each other?
Yeah.
Okay, so we make sure that at the initial stage, the two springs they're placed in like this, which means they do not repel with each other initially. Yes.
What's the purpose of using Python in your experiment?
Okay, so since as mentioned in our presentation that there are two components of angular frequency, and that's the reason why we can observe a beat frequency. So we use the Python to verify what the two frequencies are.
So you use Python to verify your own data?
To analyze our wave and find out the component side of the sine waves.
Okay, time's up. Okay, that's all.
Dear honorable judges, reporter and reviewer, and opponent from We Are Family Cultural Girls Senior High School. The proposed statement of mechanical oscillator is to secure the lower ends of two identical leaf springs to a long magnetic base and attach magnets to the upper ends such that they can repel and are free to move. Investigate how the movement of a spring depends on relevant parameters. A reporter's main focus is investigate how the movement of a spring affects by different parameters. Okay. Their experiment structure. The observation is oscillation amplitude damps over time. And in the theory, their experiments are according to EOM, and experimental setup includes leaf spring, tracker, Python, and magnet. And they use Python to analyze their data. The conclusion is that their data fits the theory. Here are some pros and cons of the reporter. Pros are that first, they have well theory and formula, and second, they change different parameters to investigate the phenomenon. And three, the theory fits in the experience model, like I just mentioned on the last page. And four, they have clear graph and well analysis. Cons for a reporter are first, it didn't show the slope of the declination of the amplitude, and it didn't talk about the changes of period. So I would like to discuss why will the mechanical oscillators stop eventually? Because the oscillator will just like this, and it will eventually stop. And what force or what theory caused the stop at last? And what's the definition of stop? Because it may just like this, and it didn't stop. And experiment of oscillation is of single wave spring. Well, I did it. I think it's good. And I would like to know, is this phenomenon related to SHM, simple harmonic motion? And how do they control the initial amplitude? Because if you use hand, you may like this one, so there will be some uncertainty. And will the period change if you change the parameter? Okay. So now I want Okay, so first question, like I just mentioned, does this experiment have anything to do with simple harmonic motion?
Okay. First, that this experience itself is not a simple harmonic motion, and we mentioned the simple harmonic motion as our preliminary model. And here we only consider one leaf spring and S system. Since we want to characterize the one behavior, then we have to consider the combination by adding the other one.
Okay, so you use EOM as your experimental theory?
No, EOM is an abbreviation of the equation of motion.
Okay, so can you talk about more about this formula?
Okay,
And
so-
how you derive it?
Okay, so X, can I use the word? So this equation here is basically only Newton's motion for X equals A, and A is the second order derivation 2 beta comes from. That is the coefficients that shows that the force is proportional to the velocity here. And as we mentioned, the V can also be written as x dot. So that is what we have is x dot here. So since this is a vector, this is a vector equation. So since the direction of the magnetic of the spring is always opposite to the one, so there requires a minus notation here. And the air resistance is also
The slow down for this one.
okay, but this one, from this one is caused by the air resistance, and as we mentioned, that the force of the air resistance is proportional to the value of the velocity, which is the speed, which means the faster you move, the stronger force you will receive.
So attending to is the whole.
Yes.
This phenomenon is related to Newton's second.
Yes, because I haven't finished this equation. So here, that baseline is the coefficients that are related. This is the proportional, so we can write as 2 beta and x is. And because it is a vector quantity, so we have to put a minus in front, so which means that it is direction. It points towards the opposite direction of x dot. So that is where this 2 beta comes from. And at last, we have to consider the elastic force, which is minus ax. And when we move them to the other side of the equation, we can find our equation and show that representation. That's how it comes.
So, how about, does this experiment relate to any energy kind of
Yes, there is
equation?
absolutely energy transformation and decay of experience actually on this photograph. In our preliminary observation, here, in our preliminary observation, we can see that the energy transfers between from one magnet to the other because one this has the largest amplitude, this one has the smallest. And we can see that the largest amplitude is decay since due to the energy loss.
So, when I'm doing the experiment, the oscillator will eventually stop, right?
Yes.
And according to my experiment, it stopped related to energy loss. So, do you agree with it?
Yes.
Okay, so you agree that the energy will loss eventually, and so okay, what will cause energy?
Okay. So basically, the damping right here, the resistance force caused by air is a factor that we have to consider. And we also have to consider that when it oscillates, the spring itself, it might experience some thermal loss, which means as it oscillates, itself it loses some energy.
So does energy loss have any effect to it?
Yes, because it eventually stops. If there's no energy decay, then it will oscillate eventually.
So let's see. And let's go back to your setup again.
Okay. So, do we still do the report?
No. So how do you fix the magnet to the E-spring?
How do we you mean attach magnets
Yes,
to the lead springs? We use the tape that can glue the both sides of the magnets.
So this is this spring and this is magnet.
Yes.
Tape you are like
Between
Yes.
the magnet and the spring.
only between the magnet and the spring.
Yes, because that's the kind of tape that can stick on both sides of it.
Oh, okay.
Yes.
I understand. So the tape is strong enough.
Yes.
So
And we also make sure that the length of each tape was identical to make sure that we can prevent some mass difference between the magnet 1 and magnet 2.
okay, so have you choose the
here. We change the coupling strength kappa by adding up the number of magnets, but we keep the total mass the same.
Okay, but if you change the magnets, if you change the number of magnets, the mass, and the magnet, of course, and the distance between them will change.
Yes, for example, as demonstrated in this graph, the red one means the magnets, and the blue one, they are not magnets initially. So when we, and the mass of these blue particles that we control has the same mass as the magnets. So when we want to add up the number of magnets, we can just replace the blue particles into magnets so that we can add up the magnetic strength, but we do not change the total mass.
So the blue is not a magnet initially, but if you need to plus the
If you want to replace, yes, you take one down and you replace with it.
Alright, let's get to the slide where I wanted to draw your setup.
Okay, we should draw by
Draw your setup just
Okay, time's up. And the opponent takes the ball and makes the sunrise.
okay, I just asked him to explain their theory and formula, and he just gave me the very clear definition. Okay, and about the sum, but it is not as simple harmonic motion that causes the oscillating magnetic. And then energy loss, they say air resistance and spring itself. Well, I agree with some part of it because actually it has something to do with friction. They use the tape to avoid the magnet to stick together. Well, no. Well, but I doubt that sometimes the tape is not strong enough, so this one, I just agree part of it. And the numbers of magnets will affect the mass. The reporter with non-magnetic items to avoid this problem. I think they do well in this part, so the mass and this.
Time's up. And we will take.
what do you mean by downstream conditions?
That the phenomenon will happen.
The phenomenon will happen.
Won't happen.
Well, as we demonstrated in the presentation, when the initial introduced the symmetry and anti-symmetry in the most model. So under these conditions, the beat frequency cannot be observed.
Okay, so you how
What do you think?
For answer your question.
So is there any boundary condition in this phenomenon that the phenomenon won't happen?
Could you give a clear definition?
Like, in what situation this phenomenon won't happen?
Yeah, sure, but I think the reporter didn't say.
Okay, thank you. So, the reporter is the effective length of the leaf string a constant or a function?
What do you mean effective length?
I'll skip to the next question. Did you consider the resonance phenomenon in your setup?
Resonance phenomena. Can you explain the word resonance phenomena?
Okay, I'll skip. So what is the correlation between the eventual stop time and the magnetic force?
Do you mean the stopping time and the magnetic force?
Yes, the correlation between the two.
Well, I believe that that was not the focus of my experience, but since that we did not consider the magnetic coupling as a damping effect, and the reason why the whole system stopped is basically because damping. So my personal conjecture is that the magnetic coupling.
Okay, thank you. So how does the opponent think?
I agree with.
Okay, thank you. So for the reporter, did you consider the kinetic energy of the magnets on the y-axis?
In our experiment, since we just mentioned in our discussion that the displacement d is really small relative to the length of the rulers. So here we only consider a one-dimensional situation.
Okay, thank you. So does the opponent think it is necessary for us to consider the kinetic energy of the y-axis?
Y-axis
Of the magnets, yes.
of magnet. Well, no, not really, because like Robert just said.
So
Their magnet initial displacement is very small, so maybe it didn't impact that much.
so you're thinking it won't affect much. So we didn't need to consider it.
Okay, hands up.
Okay, thank you.
Okay, hands up.
Honorable juries and fellow competitors, I'm the reviewer from Team Excelsior reviewing problem number 6, magnetic mechanical oscillator. So here's the problem statement. Secure lower ends of two identical leaf streams to a non-magnetic base and attach magnets to the upper ends such that they repel and they are free to move. Investigate how the movement of the springs depends on relevant parameters. According to the problem statement, we believe that we should mainly focus on how the different parameters affect the motion of the leaf spring and how to analyze the property of the coupling system and such as the eventually stop time, the beat frequency, and also the amplitude. So here's a review of the reports. In their theory part, they use spring coupling model. In their experiments, they have measurement of the elastic constants and also parameters about the magnetic force, the initial displacements. And for the pros and cons, they are very clear observation field, and also they analyze the motion and has measure of the elastic constants. For the con sides, there are no error analysis in the reports, and a lack of consideration of the resonance of the setup and the releasing method, since the base resonance that the base will vibrate together, and the lack of parameters since they have just 2 parameters in the report, and they ignore the displacements of the y-axis, and the reviewer believes that it will cause deviation. So here's the review of the opponents. So for the pros, that she pointed out that the simple harmonic motion, and also the detailed discuss on the eventually stop time, which the reviewer thinks that is critical and we need to focus on. And however, she didn't notice that the physics insights of the fitting line in the reporter's report, and she put too much time on discussing on the derivation of the theory. Also, she didn't mention the coupling motion, and which the reviewer thinks that we should mainly focus on. Also, the deflection angle is ignored. So here's the key discussion. First is about the energy loss, and the reporter and the reviewer thinks that we can use the Lagrange equation to calculate the motion of the system to get the energy loss. And for the next is about the magnet change and the mass, the change of mass. And the reporter says that they add a non-magnetical material to control the mass. The reviewer agrees with the reporter, since that when the mass increases, it will affect the motion, such as the amplitude decreases. And we asked about the boundary condition of this phenomenon, and the reporter believes that it is the initial displacement. However, the opponent didn't give us a clear answer. And the reviewer believes that when the distance between the leaf string is too long, the coupling won't occur, since that the magnetic force is too small. And there are the points that the reporter and the opponent miss. So first, they miss the definition of the bit frequency and also the amplitude and coupling. And also, the reviewers suggest that the reporter can use the Bernoulli beam model for their theory parts, since that the magnet always repels, and however the spring sometimes attracts and sometimes repel. And for the setup, we think that the reporter should consider the stable releasing method and also the resonance of the setup, since the base will vibrate together, and also the energy consumption. And in the experimental parts, they miss the measurement of the elastic constant, the effective length, and the magnetic force. Also, they miss the analysis of the motion, the angular frequency, and the eventually stop time. That is have a positive correlation to the magnetic force. Thank you.
Okay, so during this discussion, we will first start with the discussion with physics. And first, the opponent asked about the use of Python for analysis, and we agree that the function of the Python is to verify the 2 component angular frequencies that make up the frequency we observe. And the second one is what mainly causes the oscillation, and we believe it is the spring force of the leaf springs that can generate the initial oscillation. And also, the opponent asked the simple harmonic motion for one leaf spring versus the 2 coupled leaf springs. And the simple harmonic model is only used for the preliminary modeling, and then we did introduce other more complicated models. And also the derivation of the equation of the first equation of motion, which is already demonstrated on the blackboard. And we also discussed the experimental setup, the displacement, and how we make the magnet attached to the leaf springs. And for the fixing parts, that our tape is probably too straight or stiffing. But in our experimental process, it does fall us in some occasions. So we'll take the opponent's opinion into consideration to make the tape a lot more stronger. And also, we did not have a stable releasing method since we only observed the initial displacement and we released the magnets. So here we did not have a stable releasing method, but based on our experimental results, we can confidently say that the initial displacement is somehow is irrelevant to the angular frequency observed. And that's my concluding remark. Thank you for your attention.
Any questions from the jury?
Maybe I would like to ask the opponent, how would you improve the analysis? Like when you were doing it, you were saying that you should consider energy loss. What would be the difference if you were to consider air drag?
Consider energy loss. I would use maybe some application like tracker or, well, I use tools to calculate energy loss and whatever I will consider. I think just air resistance will help me modify this the experimental setup.
I have a question for the reporter. Yeah. So how did you come up with the model for the magnetic coupling?
I'm sorry, I cannot hear you.
How did you come up with the model for the magnetic coupling?
As we shown in our experiments, in our theoretical observation, we have two references at the very bottom.
Two
We have two
references.
references, and we have our idea from that reference.
I see. And why do you? I see. And why do you think there was also a damping with the linear, right, in X star?
You mean why the damping is linear?
Yeah. So
To the velocity.
right. So why? I mean, this is supposed to model what?
Yes, since in high school physics, when we have an object and when we consider the air drag, and mostly we will consider that the air drag force is proportional to the velocity.
Well, it's such a short distance. I mean, is it going to be significant? Do you think this?
I think it's no longer in short distances. When the motion, the amplitude is really small, then we can use this theoretical model that the resistance force is proportional to the speed.
Can I ask the reviewers? So you were worrying about the oscillation or the resonance of the base. How would that affect the measurement?
So we believe that it will affect the amplitude.
On the expanding
The amplitude is superposition.
Why?
Why? Because the base will vibrate together. So we think that it will affect.
Any other question? The score for the reporter 8,8,8,9. And the score for the opponent 6,5,6,6,6. And the score for the reviewer 8,6,8,7,7. Okay. Okay, thanks all of you to join this session.